this computer. Perfect. That's like, thanks for reminding me, because that's like, I would have forgotten otherwise.
Yeah.
There's one guy selecting his coffee. Once he's here, then we start. Really like 1 minute late. Yeah. I think okay. Yeah. Like unfortunately, like I need to leave relatively soon after this seminar. So, hi everyone. Today's speaker is Siegfried Louis from Penn State. Siegfried did his PhD at KTH in Stockholm before he joined Penn State in 1999, where he's now the Directive Factor professor. And he was the president of ASM International and director of the NHS Center for Computation and Materials Design. And his research is mostly on material design via first principle calculations, modeling of thermodynamic and kinetic properties, and their role in understanding defects, phase stability, and transformations. And today's talk is about something very related, about theories for cross phenomena and entropy.
Thank you. Thank you for coming. And I want to thank Professor Picker and Dr. Gareth Condensed to give me the opportunity to visit here. It's a lovely place. It's my second time to Cambridge. Last time was 20 years ago, 2002. I stayed in Darwin College for a few days on my way to York for a conference. It's very nice. And this topic actually, the first topic, cross phenomena, I started when I had my last sabbatical. So this is my 2014-15. I went to Australia and a couple of places. And they brought this problem to me. I think I solved it. Okay, 7 years. The entropy wise, we started this one about 10 years ago, maybe even longer, but we didn't get this really understanding. So for until maybe just 2 years ago, I think now I want to put them together, see how they two connect to each other. Again, my name is Siegfried from Penn State University. Okay. Well, looks like it doesn't take it now. Okay. All right. Okay, so this is a diagram. When my paper, it was we give talk in my department, and then they said, we should write an article for it. So then Materials Research Institute had virus. They said, okay, let's talk about how to write the paper. The news. Okay, the news. So this is the diagram they came up to describe what we had. So two things here, right? So the top there is the cross phenomena. The bottom is the the things, two papers actually. This entropy paper we had a little bit earlier, and cross phenomena is later. This was two together, I think it makes sense. So what a cross phenomena basically means here is that when the sun comes from the heat from the sun here, the cross phenomena produce something else. So the Earth reacts in some process, they grow the trees. Okay, then the trees grow the fruits. So that's cross phenomenon. That's what they explain. And the entropy is that if you only have one tree, okay, you can get results, right? But when many trees come together, they get some different behavior than a single tree. So that's basically the entropy means. So they think this would be good for the general public. I don't know what works or not. But anyway, they put this news out actually just 2 or 3 weeks ago. I can do. All right. So then what we really talk about is what if we looks like this we can take it now. Okay, that's good. So actually, when you talk about cross phenomena, there must be a directive phenomena, right? Because you have direct and indirect, so to speak, basically what I meant there. So if you look at what we typically talk about is the temperature. If you change temperature of a system, you will get some direct effect. Maybe I should test the student. What's the direct effect from temperature? If you change temperature, right? Heat conduction, that's right. The direct one is heat conduction. So what would be the cross one? Sorry?
Thermoelectric.
Yeah, that's thermoelectric is perfect. That's exactly. So the electron moves, right? Okay, something like atomic diffusion, you got a volume change, right? That's the indirect. That's cross phenomenon, basically. They call it. Well, I think it's good term. Then if you think about it, you put electric field. The direct one will be the electron conduction, right? Okay. Then you get this electric current. The indirect one is that you will get the heat conduction. You get the atomic diffusion, like a strain. So it's basically, of course, you can do magnetic too. That's one. But it's basically the one. But if you make it general, so what do you change from outside? If you look at this first two, you change, you make it very general. You say not a temperature, not a field, not this one, but you will call it the potentials. So you change the potentials, and the system going to react. Direct react would be a property, and the indirect by the corresponding another one. So you get two types of behavior. So you get a potential gradient that you apply. You can apply, if you think about it, you can actually apply four types of, right? You can apply the temperature, electric field, magnetic field, and the stress or pressure. That's when you apply. And then direct the migration of something change in the system migration. Then you get a direct one, is a conjugate variable. Conjugate variable means it's in the thermodynamics, there's pairs. If you put them together, they produce energy. That's the direct one. If they do not produce energy, that's indirect one. So that's basically the concept of putting together. Yes.
No, this is very helpful. So in that general definition for the external potential gradient, it sounds like you've taken a quantity, then you've integrated it, in that case, with respect to space, and then you've differentiated it again. So potential sounds like an integral, and then gradient goes back down again.
That's right. So
so there's two steps there. Can you do something even simpler? You could have put an external potential there. So you just do one integral. Would that also be the direct?
Direct has to be inside. Right? What was respond from inside, right? External control would be apply a field. So if you apply a field, the system will react to it. So two reactions can happen. One is direct reaction. Then that one react, one will produce energy. The other ones will not produce energy.
So for electrical field, then the thing that would often have units of energy would be the electrical potential, which is just an integral. Whereas the electrical current is an integral and then you differentiate it again if it's a local field.
Let me wait. Next slide, you will see.
Okay.
That's exactly what the problem we had before. So when I was introduce this one, of course, I get this equation, right? Onsager's equation. Everyone says Onsager's. What it means is that if the flow of a quantity would depend on all potentials. For example, you can potential of temperature gradient, electric field gradient will all affect the potential, the flux, right? So that was the Onsager proposed in 1930s. And then he made another step further. He said, okay, now if you believe that equation, and then the coefficient would be symmetric. Because that's what it means, right? For example, you put a temperature gradient, you have electric current. You play electric current, you're going to have heat conduction. And he actually derived it, but not from fundamentals. He derived that the coefficient should be symmetric. So the temperature go to heat, the current go to temperature, electric field go to temperature, heat conduction should be same. You get Nobel Prize on that. Okay. Of course, I'm not. So, but this is very important. This equation is completely phenomenological. It's just that understanding. You say, okay, I should have this relation. So he proposed that one and derived it and proved it phenomenologically again. But if you look at the literature, this is from here. It's my professor in Sweden. Is some of the next slide. He said, this is not from fundamental physics. It's just the observation you drive the equation. It's like Ohm's law and this kind of fixed law kind of thing. But of course, we say Ohm's law is right or not. We can discuss that. Of course, it's right. And then another paper says, a book says that it's not from law of thermodynamics. Okay. So then I said, maybe I should derive them from thermodynamics. Okay. So you can see that's right. It says phenomenological. It's proved by concept, not by rigorous derivation. Okay. So then I thought maybe I should solve it. So that's what 7 years ago, I decided to pick it up and see if I can derive it from fundamentals. Okay. So some question on this one actually is kind of a mathematical question. Is that if you think it's symmetric, you can diagonalize it, right? If you diagonalize it, there must be just an eigenvector left. So what is it? What are the components of that eigenvector? Actually, this problem, of course, is not new, right? As soon as the theory was, the postulation was presented, and the many people discussed, something's not right there. Not right, okay? Of course, there are actually a lot of papers published say it's wrong. Like it's wrong. But even more important question is, in my paper, I had a few questions. This is just the most important one. And then if you can do that, okay, that means you get this eigenvector, can you just derive it as an eigenvector? Instead of go through this process, go inverse. You assume it's symmetric, and then you go back and find it, right? So why don't we just start from the beginning? Can we derive it completely? Of course, I showed that already. If you see my first slide, actually we can derive it, second slide, because it's energy. Remember that? Everything is energy, right? If it's not energy, it should not be in there. So it's actually, that's what I started with that. So what I did is that, so look at the first law, okay? So below the first law like this, right? du equal to dq plus dw. This is for closed system, okay? That's not good. So we should do the open system. Open system. So it's very, very important that people talk about thermodynamics for equilibrium system. Okay. But however, this two equations did not talk about equilibrium or not. So it really doesn't tell you what's equilibrium or not. Okay, you can talk given works. Right? Given work, we talk about the stress. I didn't put a magnetic field here because I thought it's too complicated for me to work on. So I think the simple ones. I think this is the ones to work on. And then there's no information about system, is equilibrium or not. So that means the thermodynamic first law actually doesn't care about if it's equilibrium or not. Okay. But it says, why do we believe thermodynamics is for equilibrium only? And that's what's come to second law. Second law again, we start with this one. Canonical cycle is closed to equilibrium system. So that's important. So when you start this equation is closed to equilibrium system. That's first definition start this equation. Of course, as we showed before, you don't want that, it's the open system. So if the open system, you take mass and put mass in there, the mass has entropy. Okay, so you have to add one more term. But even more important, if you say it's an open, non-equilibrium system, then the entropy becomes like that. So it's three terms for the entropy. So you have the heat, as we used to talk about, and then you have the mass, then you have the internal reactions. So that's really the second law. Second law is really the last term only. Is that any internal process, if it happens, it has to produce entropy. It doesn't matter how your system, whole system behavior. It's that a process itself has to produce entropy. So, any questions on this part? Okay, now you see that the Q is in both the first law and entropy equation, right? So basically, we did that's what Gibbs did. So you move, of course, in the Gibbs equation, it doesn't have the second and third term, only the first term. That's for equilibrium. That's for equilibrium closed system. There are two problems with that equation. One is the chemical potential definition. It didn't define it, just take it on at the later. So it's not define what a chemical potential is. And also it's for equilibrium. Okay, if this one, then you got the combined rule like this. Now you introduce chemical potential. Chemical potential now is basically the mu I minus TSI. So it's a very clear definition for chemical potential. You don't need to just add on if you look at in the literature. So what Gibbs did, he said he's interested in equilibrium only. That's Gibbs equation. So Gibbs derived in 1800, 1871, 71. And he said this is equilibrium. So the system drops, you can see the equation. Actually very interesting, right? If you drop this one, entropy, right? Actually it has two terms now instead of three terms. Now you can separate these two terms into two quantities. One is called potential, another called the molar quantity. So potential is what drives things happening, and the molar quantity was moving, was changing. So that's combined law by Gibbs. That's his, if you go back to his paper. And I have one slide to show connect to Cavendish lab. The first professor, Maxwell in next slide. But if you want to make it into the general form, non-equilibrium, so I have to keep this term, right? Keep this term, that means you have something happening there. So if you can have many processes happening, then the driving force times that change that process. So you can decouple it, you can make it independent processes, and each one has driving force will be the gradient of, not gradient, the difference of one of the potentials or the combined potentials. They have the change of a corresponding molar quantity. Then molar quantity could be a combination of many species together, or few processes combined together if they're not independent. And this book is my book, and all the thermodynamics in that book is part of the Cambridge University Press in 2016. Okay. I am working with them to do revision because cross phenomena was not in that book. So I want to put that cross phenomena in that book. Now this has not talked about how to calculate flux here, right? Now, but we do have this one now. This is one internal process. You have the driving force, you have the process of that internal process. You can call this one into minus potential difference times the molar quantity change. Okay. Now it's important, these two are conjugate variables.
So I'm not so familiar with these y's and dx's.
So why is it, why?
Like, if it's possible to say a couple of examples. So if I just do the simplest bit on the left, which is dw.
Yeah.
If I was doing some work on my system,
PDV.
which, yeah,
That's right. So that means, for example, you change the P pressure, right? You change the pressure, you get a pressure gradient in your system, then the volume is going to shift. So that's volume change. If you change temperature, entropy will shift.
So even though I think you called y a potential, and I might be tempted to think that W was a potential.
W is not potential. W is energy.
So
Actually, in textbook, they call it thermodynamical potentials, which I think is confusing. Yeah, if you separate them, then it becomes clear. You have T here. It's the T is the potential, pressure is potential, electric field, magnetic field are potentials, and chemical potential. Right. These are all potential because they drive changes.
So in the final sum, you have the delta y and dx, which is like product of two changes.
Yeah, entropy reduction of that process.
Okay. So what is the delta y here?
This one?
Yeah.
Yeah, this one, for example, it could be temperature gradient times your entropy difference, entropy change.
Okay.
Or it's
So you basically integrate it with respect to dx.
Yeah, it's just the dx is one of those variables, and the corresponding one in front of that variable is what the potential you have. So it could be temperature, entropy, pressure, volume, and the chemical potential, mass, and the electric field, electron.
Where electric field will be the gradient of the electric potential.
Yeah, exactly.
This is some other words I just about remember from my time doing thermodynamics. Was intensive and extensive.
Oh, that's again not a good term. It's not a good term to use. I brought it in my book, that one. The reason is because mole fraction is intensive, but it's not a potential. Right, normalized. So the intensive and extensive variables are confusing. It's not unique. Yeah. But if you just use potential and molar quantity, then it becomes unique. It's not confusing. That's why.
Yes, I think all the examples you said, but previously, my thermodynamics lecturer is now retired, but
yeah.
I'd have said y is intensive, yeah, and x is.
But x could be intensive too.
So you just give an example of that.
That intensive variable means that it's size independent.
Yeah.
But mole fraction is size independent.
So the examples that you gave about pressure and volume or
volume is not absolute volume.
The pattern intensive, extensive.
That's why I avoid them. I want to use potential and molar quantity, and there is no confusion about that specific one. The normalized molar quantity are also intensive.
Okay. Thank you.
Good. Yeah, that's actually, I try to avoid that in my book. That's really, I think, that's confusing. When I was an undergrad student, that confused me a lot. Yeah, confused me a lot. That's right. Okay, so now we get this equation by Gibbs. This is Gibbs' famous equation. TdS minus PdV because it's talk about hydrostatic pressure and the closed system. So you get the equation U is function of SV, right? Okay, that means SV determines U. And then when his paper was published, and published in Maxwell, that's the first professor here, and he read his book, his paper, okay? And he got very excited. So he decided to draw the three-dimensional diagram, USV, right? Three-dimensional diagram by hand. Make the model. He made the model. He sent the model to Gibbs. That model now is in the United States, in I think Cornell, Yale Library, okay, as a model. Okay, it seems that just before Maxwell passed away, and he got the model in the United States. So it's archived there now. It's pretty interesting.
But there's a copy here.
It's copy here too.
Yeah.
Where is it?
Downstairs.
Oh, I should go have a look. Take a picture. Let me take a picture of it. It's still here too?
Yes.
Oh, it's fantastic. Fantastic. Yeah, I didn't know that. Okay, so now we got this. Suppose you agree with me on the thermodynamics now, right? So I'll move to the kinetics. That's what I did last 6 years. So I want to derive the flux and driving force for the equation I just had. Remember, I have this DIPS, right? That's the minus delta y times dx. So now I can start this DIP. That's the entropy reduction in that one of the process. Now I can do the rate of it. So I say that the rate of entropy reduction, because we need to get a time into it, right? So then divided by delta V, that's volume, small volume. Okay. So you need to put T there because T times 1 gives you energy. So it's not entropy production, it's energy production. And then you can just do the equation to volume. If you think about a slice, the volume you could do one is small volume is the area times delta Z, the distance. And then you change the DIP to DJ, T times DIP to DJ. And then just shift a little bit. You got Y here now, right? Y and X here. So dx, that's the mass change rate, divided by A, gives you the flux. And then the delta Y divided by distance gives you the gradient. So I think I derived it.
Do I need to be concerned if the volume is changing with time and it's?
Oh, okay. That's actually a very important point because at the end, when you solve the solution, it's steady state. At the end, when you solve the solution, when you get a solution, use steady state, so the volume doesn't change anymore. Yeah, at the beginning, at the transient state, it does. Okay, but so all the equation we use when we get solutions, we talk about steady state. So its volume is not changing anymore. Yeah, during the process, it does change. Because at the beginning, the volume is homogeneous, right? As soon as anything happens, the volume will change. Yeah, so absolutely true. Oh, so I was very excited. I divided this one. Then I thought I solved the problem, right? So I tried to move it forward. The flux, right? Flux. That's what you have to think about how to do flux now. Flux is a defined definition here, okay? Then you say the flux is proportional to the linear function of the gradient. Okay? So that's an approximation. People still cannot do that because not all systems are linear, right? It's non-linear. Of course, most systems are non-linear, but that doesn't matter because you can only make it delta Z small enough or delta T small enough, then do integration, do path integration. If you do path integration, you will get the results. If you know the path, right? You know some energy change along the path. So you can always make the time or Z as soon as possible, make it a local linear function. They do integration for that. The important thing is that if you think about the entropy reduction, that's our entropy reduction, right? So you put this one back there, then calculate the entropy reduction. That's beautiful. The big entropy reduction is its L is positive, that's the kinetic coefficient, times the delta Y squared. As always positive. If anything happens, it always are positive. It always produces entropy or produce energy. In this case, with temperature types entropy reduction, produce energy. So I think I solved the problem. So I solved the problem which actually in the positive community for quite a while, which is still, I'm sure not everybody agrees with me. That's for sure. Okay. Because they don't find a solution. No, I think I'm very happy. So now we're going to apply it, right? We're going to apply it to all cases. All cases. No. Any questions so far? Sounds unreasonable?
What's the simplest version of this formula? Is it
Next slide. Next slide.
Oh, yeah, I probably missed, I'm sure you said so, but why is L positive?
Oh, is it because if for a stable system, the flux is always from high potential to low potential. Is for unstable system, it's different. It's negative. Okay, for unstable system, this guy could be negative. Yeah, but for stable one, it's always positive. Yeah. If for unstable one, then this all doesn't work, right? You don't have linear function anymore. It's a stochastic, complete stochastic. Okay, but before I want to move forward, that's theory now. Okay, so theory is that, so this equation, flux equation. So flux equation, so the answer equation is wrong, basically. Okay, answer equation is not. Well, I would say it's wrong. It's like if it's symmetric, you can make it a diagonal. Okay, if you get a diagonal, that's the equation you have. Okay, so the driving force is completely determined from the combined law as the front term, and the flux will be the dx variable in that combined law. So it's derived from from combined law, the flux equation. The only assumption linear function. That's the only assumption. But I said you can always make a complex function linear to integration. Okay, now what's cross phenomenon? What does the cross phenomenon comes in here? Right? Now it's delta y here. The delta y is a potential function of all variables, right? So it's not only its conjugate variable, it's the conjugate, but also another potential or another molar quantity. For example, the chemical potential gradient is a function of entropy, is a function of composition, is a function of volume, it's a function of everything in the system. So that means if you want to evaluate it, then you can do this kind of decomposition. You can say it's a function of its own conjugate variable. That's like fixed law. Okay. So fixed law is not general. Fixed law is not the potential, right? It's not the potential. Fixed law is composition. You can do that one. But then you have to also do the derivative of this y to another potential. Then you got the integration of another potential. Then you can do that to another molar quantity. You can do that with another quantity. So that's what cross phenomena are. It's just the conjugated potential dependence on other quantities you have in the system. So this basically is cross phenomena. So the flow of a molar quantity with dx is completely driven by its own potential gradient. The cross phenomenon is just the dependence of that potential to other potentials variables. So to experiment, you see that, but when you put the equation back, actually it's not the way you would do. You should do this derivatives.
Yes, if there were three terms here, your definition is pulled out one of them, the first term, because it's the J is common.
That's right.
Side J is common. But then you've got these other two terms, which I would also see might. These are different with respect to x and the other with respect to y.
Yeah.
Give
example, right? Give example. Chemical potential and atomic diffusion. So the chemical potential, right? Gradient of one species, one particular element, is a function of its own composition. It's a function of temperature, pressure. It's a function of another element.
And so that you're going to sort of subdivide the cross phenomena, sort of title into two titles later to capture those two different pieces of physics.
Because that's what you do experiments. You measure this one. You don't measure that one directly. You measure other ones, right? So that's what people. That's what actually I think it was answered phenomenology questions about. You do experiments. You find that if you change this one, that one changes, right? This one must be proportional. That's right. It is. You have to do that. But it's not to put all the potential together. You have to do like this. Decompose it.
Does it mean like it assumes that the y and x they're not coupled with each other? Is it like the universal assumption?
So all these quantities here are independent variables in the system. Independent. You have to be independent. If not independent, you have to combine them together. Yeah. For example, there's one case, for example, when we talk about diffusion, right? if all the elements, the diffusion is very slow, you combine them together in one element. They behave like one element. You don't have individual chemical potentials anymore. So it's really the independent variables are the key. That means you can control them either from outside independently or internally they're independent. Okay, now go back to your question, the example. Oh, before, too many theories. Another one is actually, another question is about this linear function, right? So you got it. Actually, the equation we have here is already second derivative, right? Because this first derivative here is the second derivative of potential energy. Because this is the first derivative, another derivative is the second derivative. So if it goes to the third derivative, okay, that's what we talk about instability. And actually it's a critical point. So when second derivative goes to 0, that means there's no cross effect. Okay. But if the third derivative goes to 0, it becomes a critical point. So that excites us a lot when we understand this one. So that's what the divergence of the property comes. That's called emergent phenomena. Okay. So that means the behavior becomes so dramatic. If you go to extreme is that when you lose stability, unstable, then this pair, this conjugative pair goes to 0. From positive to 0. That's the thermodynamic stability criteria. If this goes to 0, if you inverse it, it becomes infinite, right? So it becomes infinite. But this is because it's positive before, positive becomes 0, positive 0, and the important inverse becomes positive infinite. So that means if you temperature of entropy, if you swap it, so entropy to temperature becomes a positive infinite. Entropy diverges, volume diverges, all the quantity diverges at a critical point. Nothing, I didn't understand it until actually a couple of months ago. How about the mass divergence, right? So think about it. If the mass, if it's n to chemical potential, it can be diverged. How could the mass diverge? I didn't realize it before until I learned this quantum critical phenomenon. At a quantum critical point, the effective mass of electron diverges. It's like several order of magnitude higher than the electron mass. That's actually mass divergence. I'm excited to learn that one. So this conjugative variables is positive, but it's long conjugative variables. For example, temperature, volume are not a pair. So that means it could be either positive or negative 0. So that means if you inverse it, it could be positive or negative infinity. Divergence could be positive or negative, either way. That's we did that before, but we didn't understand why it does that until pretty recently. Okay, now if you put all of them together, so we got our molar quantities, I got our potentials. So their relationship is the first derivative, right? The first of energy to temperature derivative give you entropy. The internal energy derivative of entropy give you temperature. So the row and the top and the left here are the first derivative. Then in the middle is our second derivative. Second derivative in the middle, in the diagonal side, is this their conjugative variables. So they are all positive. Now positive. Inversion is positive infinite. However, the all diagonal ones, which are non-conjugative variables, they could be positive or negative. So the nature does that. Nature sometimes make a one positive, sometimes positive, sometimes negative. So that was actually, if you look at the literature, we believe that we are the first one to give the fundamentalist interpretations why it becomes negative. Okay. Why it becomes negative. And then another one which has, I want to go back to this equation here. This say that blue here, the blue quantities was not discussed in the literature much at all. For example, this one, this is interesting, right? The mass to temperature derivative. So how does this one go to infinite? And then another one's mass to the elastic field and the electric field and magnetic field, even to the chemical potential, right? They can all diverge. That has a positive for many, many years. I don't have an example of how the mass can diverge. That's very interesting. And mass can have negative divergence too. The mass can go to negative infinite. This one actually, most of them, except the blue ones, are already in textbook. Even though I still remember when I was a student and the professor said there's no use of these quantities. Nobody's using it, okay? Nobody uses relations, but sometimes it's very useful. And the next one is
So
not,
that one you said the most sensitive one, the mass to electric. So is that like a capacitor charging? It's not like a capacitance.
capacitance.
Something.
But
Well, it's up at more voltage.
Yeah.
Across the capacitor, I get more electricity.
what I'm understanding now is that this is actually not the mass itself. The total mass is not diverged. It's that component diverge. So what it means is that that component actually sucks all the components come together, make a big component. It's like chemical reaction. It's really chemical reaction happening here. Okay, chemical reaction basically means that if you think about this one, right, it's having a polymerization. What happens is that the system will suck all them and make one molecule. So that molecule's weight is huge compared to other ones. That's what my kind of understanding of.
It might just be like an electron and a hole on the other side of the capacitor with a little electric field line between them.
But it still doesn't increase mass, right? It doesn't increase mass.
Really, it is.
And I looked at literature is that the best example is it's actually all of them. This one, and that one, and this one too. You know, in the quantum critical phenomena, if you change the magnetic field, if you move close to the critical point, and the effective mass shoots up. If you go away from it, it goes down. So it's basically that effect.
If there's on quantum critical phenomena, then there are these scaling relationships you can get out. Have you explored those?
I haven't done yet. I hope to work with somebody here. So we can work on that. That's fantastic. That is fantastic. Yeah. That's a perfect example I found so far. Yeah. Okay, so this has been discussed, but this one's never discussed before. Right? That's the two potential derivatives. So that's actually the cross phenomenon. Right? So for example, the atomic diffusion is driven by chemical potential, but the chemical potential is affected by temperature gradient. So that's cross phenomenon. So that means this one, right? It's thermal transport. This stress transport. This is electric migration. This is magnetic migration. This is cross diffusion. Turned out we kind of have this observations, but we never use this one. If you look at literature, all these quantities, people believe they are kinetic coefficient. So all the cross phenomena in literature, how to solve the function, right? How to resolve get a solution, you try to do the kinetic simulation. You do Boltzmann transport theory. You can do that. But turned out we don't need it. Okay, that's the big example we have. And even more interesting is that this is very easy to measure, right? You put a temperature field, you measure diffusion, right? It's very easy to measure. However, on the other side, you can very easy to calculate. So this is Maxwell relation. Okay, it's a Maxwell relation. It's beautiful. It's really combined the experiment with theory. Okay, so that's the theory because of course I focus on entropy, right? Entropy, because temperature is one of the primary controls most. Okay, so it's beautiful combination. When we realize that you have a beautiful experiment, each to do the experiment, each to do the calculation. So what it means is that, well, we claim that all this calculation people did before is, I wouldn't say incorrect, but it's huge approximations which is did not capture the fundamentals. Okay. Of course, you can always do the experiment to measure the atom moving, right? You can do the Einstein equation, get the mean distance, get diffusivity. Of course, that's always right. Okay, but you don't have to do that. Okay, what do you have application? TCP kind of theory of cross phenomena. Okay, so the key one here is that it's a so if this atom, this molecule is moving like the diffusion, take diffusion as an example, driven by temperature. It's because the chemical potential of the atom is affected by temperature. Okay, that's called cross phenomenon. So let's take one example, temperature, right? Or the temperature change. So temperature, when you have some electricity, what it is the temperature gradient affects the potential of the electron, then drives the electron move. Okay. So that's what cross phenomenon is, that temperature changes the potential of electrons, the electrons start to move. is not temperature driving electron itself. It's because temperature affects the potential of electrons. And diffusion is the temperature affects the chemical potential, then drives the atom movement. That's basically the idea we have. And of course, you can talk about if the electrical field, electromigration is the electric field affects the chemical potential, drive diffusion. Yeah. And the temperature gradient, right, is affected by the electric field, drives the heat entropy diffusion. If you have stress, there's some electromechanical behavior to ferroelectric materials is that you apply the stress, then you start to change electron potential, electrons start to move. So what it means, the important thing is that means if you got thermodynamics, you can calculate all of it. You don't need to do the diffusion, the kinetic process to calculate. Okay, we did example of Seebeck coefficient. If you look at literature, Seebeck coefficient has always been calculated by actually falling electron motion. Okay, to do that. But for steady state, it's a zero current. You can calculate. So what is that? It's actually a partial entropy of electron. So the derivative, right? The derivative is the mu to t derivative. If you change to the on my table on the other side, would be entropy of electron, entropy to electron, a number electron derivative, and it give you the partial entropy of electron. That's well defined, perfectly defined thermodynamic quantity. Okay. You can do same, and you also see that the Seebeck coefficient is negative, but because electron has a heat, right? Carries heat, so at the same time carries the heat conduction. You put the two together, you get the Peltier coefficient and the Thomson relation directly from this relation. And if you change to electron in the holes, you get the positive Seebeck coefficient because the voltage you change direction. Okay, so we did calculation. Use our model. Use our DFT calculation. Get electron density as function of temperature. You can see this. You get the -1 by doping. You get a positive one. You get p type of n type. Then paranoid. And it's the lines are predictions. The symbols are from experiments. And they can do the tin selenide. And in the literature. Is the dashed line here, the Boltzmann transport theory prediction. Is no way to match up there. The reason because there are two parameters in the Boltzmann transport simulation. Relaxation time. That's one of the big unknown to do that. We also do this lantern telluride for different ones, and the agreement is amazing. It's unbelievable. There's no feeding. Oh, well, we have to use DFT to calculate electron density, electron structure. Okay, now I want to spend a few minutes talk about entropy. We need to get entropy, right? We need to calculate entropy. Okay, and if you think about what entropy you learned as you before, you do experiment, you measure heat capacity, you get integration, get entropy. So that's the experiments. Everything. If you look at statistical mechanics, you take a Gibbs distribution, it's a pk log pk. Pi log pi summation, that's Boltzmann too. It's actually Gibbs one. Gibbs derived that equation in his paper. If you go to quantum mechanics, you got majorly two, actually a three now. When literature, one is some electron, you got a Fermi Dirac statistics, you got a phonons, you got a Bose-Einstein statistics. You can people have one more here now, which I don't know how to deal with, is entanglement entropy. I don't know whether that's included here or not. I'm not so sure about that part. But anyway, that's what we have now. And we have these three entropies. What do you mean? What's the relation here? If you look at the statistics, they only use this one. Okay. If you look at the we do quantum mechanical calculation, look at this one. What do you explain because that one? What's the relation between them? That has puzzled us for a long time. At least me, long time. How can we put them together? So if you look at that's what we develop an approach. Then okay, you look at the system level. You say you have so many configurations. You get a pk log. This is a Gibbs distribution. Okay, minus kb, pk log pk. If all the pk are the same, you got a Boltzmann equation. It's kb log omega. Right? And then you have a lot of different microstates. If you do that one, what it means? If you take that equation alone, that means all the microstates has zero entropy. But we know that's not true, right? Even the quantum state will have so many entropies. So that means each of them has another entropy, right? So each of them has entropy. That means you have to put them up here. So this is basically our equation. So this first part is the statistical mechanics. Okay. Second part is quantum mechanics. So this entropy of the system it has two components: statistical mechanics part and the quantum part. So that's of course you can make it even down further if you do that. Yeah.
And presumably, if I was calculating the entropy of the solar system, could it be that the first term will be the entropy of each of the planets in their orbits, and the second line blue would be the entropy within a planet?
Exactly.
So it's not
Absolutely true. That's exactly the point of people missed in the literature completely. Because you see, when you talk about the planet system, you only talk about the planet configuration. You forgot about the planet itself. That's why it's the big error we have in our entropy calculations. Okay. We actually found that in our calculation here, if you forget the second term, your transition temperature is 100 to 200 degrees off. If you put the second term in there, it's 5 degrees off.
So I've not just thought about this before pursuing that, but presumably if I replace the SK with some other P or P sum,
Yeah, it is
put it together, then do I inside the log get some P's multiplied by P's, which would be how I'd combine probabilities if they were statistically independent?
Exactly. If you can start from the bottom to all of them, you don't need this stuff. Because the Fermi-Dirac or Bose answer is all Pichet style equation. Or similar equation. It's a bit different, right? But it's all similar equation. It's all Pichet today, it's small scale. Exactly. So if you can sum all of them, it's perfectly okay. But you cannot do that. Okay. So that's why DFT becomes so important. That's why DFT works. DFT take one level, everything quantum that just happened and I put on top of it.
Yes, and this combining together works if it's with getting a product of P's is going to be fine, provided these are statistically independent, which is hopefully the case if they were truly separate systems.
That's right.
That don't talk to each other much.
That's right.
Okay.
Exactly. Beautiful comment. But you can make it even lower, even higher, right? That's why I work with Will. I'm talking with Will already. We had one meeting. I wanted him working with me together to get the black hole. I want to connect to the black hole part, see how that works. Okay. So now, but however, if you look at the typical statistic mechanics, so we told this entropy, this partition function, right? That's what we have. The total energy here is not free energy. That's perfectly okay if you consider all possible configuration states. Okay. But if it's not, then you need to use the entropy one. Is that you need entropy have the actual term there. If you do that one, what happens? Your partition function will be Fk instead of Ek. So if you take this equation, decompose it as this equation. If you take this equation, you move down to that equation. So these two equations both are correct, just like what Gary just said. They're both correct. So how can it be correct? Is when this guy equals 0, right? If this equals 0, evolving equals 0, both equations the same, right? So when can they be 0? Is pure quantum state. If you can sum all pure quantum state, then two equations are identical. Just like what Gareth just said. Because if you can decompose all your phonon configuration, electron configuration, so put individually together, you get the first equation. But if we cannot do that, okay, you cannot solve them. The equation too many. But if you take a DFT as a base, then all the DFT calculated entropy will go to SK. And then you cannot use EK anymore, you have to use FK.
So would another perspective on this to be sort of, I guess, viewing it as a clever way of rewriting the sum on the left-hand side, right? Like it's a sum over all possible microstates, but if you then take the whole enormous microstate space and sort of partition that into the Earth state space, the Mars state space, the Jupiter state space, and sort of lump them together.
Exactly.
That's, I mean, and sorry, am I missing something in the technicalities where there is an extra term that's small that's being ignored, or is it actually just an exact rewriting, relabeling of the states?
I think the answer to that question is that you want to make sure your states are ergodic. You basically carry all the fundamental states, but you don't need all the states. That's the key. if one state can be combined, is combination of other two states, then you don't need that one. So it's really the independent states you have will be sufficient. Yeah. I'll give you one example. So the equation is really that the first one is based on our understanding here. This is the DFT part. Okay? And the second one, you put a statistic on top of that. Then you can compare with the experiment. That's the only time if you take this one, you cannot compare with the experiment directly. That one, not easy. You have to put them together, then your heat capacity entropy will be agree with the experiment. So now if you believe that one, okay, they can start applying now. You can predict the emergent behavior. Either two combined together, you can do that. And you can predict singularity. You know, Steve Hawking about singularity of this big word, singularity, right? I can predict it. Okay, now I'll give you two examples. The Sirius is a very interesting element. And 0 Kelvin is non-magnetic. The high Kelvin is ferromagnetic. That's the only one element in the periodic table that does that. It's a crazy one. No other element does it. Right? Husbands is always AFM, FM become paramagnetic. It's only one element from non-magnetic to paramagnetic. Okay, we only need 3 states. Answer your question. We need only 3 states: non-magnetic, AFM, and FM. It's completely predicted the critical point. That's the singularity, and all the experiment data from the literature. That's the temperature volume phase diagram. However, if you want to do the Einstein pattern, the 3 states not enough. We get 500 states to do it. Again, the experimental prediction here is that you see the experiment is the volume increases, and then volume starts to increase less and decrease, right? And then increase here. So you see that this range, you have the emergent behavior. In that range, you have the emergent behavior. Everything else, every other places are normal. Okay. So why they are abnormal here? Because computation of these configurations is computation. When the computation becomes so severe, they become unstable, singularity. So 3 states actually is enough to reproduce this case, because you can think about this one, any 2 combination will generate some intermediate states, right? So that means you don't need those intermediate states to describe the behavior.
So I was probably dating, didn't quite catch what you did here, but for your theory, you started with 3 states and then had some fitting parameters.
No fitting. Take 3 parameters, 3 structure, calculate the phonon.
Oh, so you did some DFT calculations.
DFT calculations.
Calculated some phonons.
That's right.
And then
put them together. That's 3 terms, right? DFT and the statistical mechanics, then the experiment on that side. Okay, so now the reason is why could it be positive or negative, right? Is this negative divergence, positive direction? Positive divergence is because T and D are not conjugated variables.
So another question for that DFT, I'm probably asking half the times and bit strengths here. But they sort of had work on anharmonic phonons, which I might imagine is important around these critical points. Is that necessary for you to consider?
It's not important. Okay, maybe Chris can agree with me. Yeah? Let's see. So the largest harmonicity at this point is not because of individual states at all. It's because the peak of computation. It's longer there. It's changed dramatically. So I believe that unharmonicity, in my opinion, is mostly because of these statisticals, not because it's itself. And here, all 3 of them are quasi-harmonic. You need quasi-harmonic, of course, right? But you don't need unharmonicity. At least there was 2 cases we have. And not only 2, we have many cases. One is we have pure iron. I think I talked with Tommy yesterday. He had BCC iron too. So we're going to compare. He used DMFT. We're going to compare with that. So we calculate the PT diagram, right? The magnetic transition for the pure BCC ion. We did it for FCC nickel. And there's some experiments here. This is some experiments here, some experiments there. And then we also did it for this, not superconductor itself, but a superconductor base structure. And we did the spin density wave AFM change here. So we take some criteria. We said if 50% of them is the spin density wave AFM structure, it produces this line, and these are the experiments. You also keep that's called the characteristic temperature. When we say 99.99% of the spin density wave AFM, that's the low, that's ground state, then you get this state prediction. So that's why there's lead tablet, which is not published yet. We have been working on this one for 10 years. We cannot get the value. We don't know how to do it. I didn't know how to do that. So
Sorry, in the last slide, what is AFM stand for?
it's anti-ferromagnetic. Anti-ferromagnetic. You're welcome. So that time, if you know you work on ferroelectric, you know it's ferroelectric, paraelectric, right? Paraelectric is cubic. Ejection is cubic. And the ferroelectric is tetragonal polarized. And it turned out, if you do simulation, you find that it's always polarized. It's a high temperature too. And somebody experiment found that if you do the very fine experiments, there's no cubic. Doesn't exist cubic. Okay, but if the X-ray, it's all cubic. Okay, that's just resolution issue. Okay, if you look at the atomic scale, actually it's all this domain wars. You have 180, you have this 180 degree, you have 90 degree. So then we say if we take this value, now we have the tetragonal polarized one, right? Ferroelectric. Then we have the two domain structure. Put them together. You predict the transition temperature. Okay. So now of course it depends on the domain or energy, right? We take two sets of data from literature. 35, 132, that's 35 for 90 degree, 132 for 180 degree. You see that it's dominant in 90 degree. The transition is 77.6, okay? And the experiment is 77.5 degree. It's 1 degree off by experiment. And then if we take another value, this is a new value, okay? This is from Mandelbrot's group. This is from other groups. So I trust the available state of and this is about 100 degree lower, 100 degree lower. So the DF calculation is very, very critical. So most recently we have paper just submitted for each nuclide. And this one is very interesting because as I mentioned yesterday to Chris group, these people believe this transition is a strongly correlated physical phenomenon. Okay. And you know, I'm not a physicist, so I just try if my method works. And then Alex Zanger, his co-author, and he said, Zico, you should work on this one. Each nucleate. Okay, let's do that. It's a very complex structure. Very complex structure. So I have a lot of configuration we have to do. If I take 80 atoms to do that, it's a lot of structure. But if you take all this possible configuration, spin configuration into it, let's predict the transition temperature as function of pressure. The red dot is experiment. There's no feeding parameter again. No feeding parameter. It's complete DFT calculations. Got the phono of all the structures. Is the equation have the two parts add together. You get this phase transition. And it's even more interesting is that you see, I was thinking when at the beginning I said, you know, it's go up here, it should continue to go up, right? But then I realized in P1 that goes back too. This one turns out it goes back. You see, and it goes back. So that means that these two places, you're going to have some critical phenomena there. I think this can also predict that too. But we haven't, that's one thing I want to learn from Chris here. That I want to see at 0 Kelvin, can we differentiate superconductor, non-superconductor, superconductor, metal, semiconductor insulator at 0 Kelvin without a temperature effect first. And then if we can do that, we can take the phono of each configuration and predict its transition temperature. As function, superconductor transition temperature as function of composition, pressure, like this. All right, I think that's my last slide. And I do want to mention that this can do information to you extend this equation a bit further. You got the heat generation, you got the nutrient consumed, and you got the waste generated, you got the information production destroyed. That's why I was working with the guy from Department of Ecosystem about forest. He wanted to talk about the forest. Entropy budget, he said, how to decide if this forest is bad or worse, and do something about it. Yeah, that's pretty interesting. All right, what is the summary here? And I hope I convinced you, or at least you have some idea that the flux can be derived from the first law and second law without any phenomenological assumption on Saga had back many years ago. And now we can calculate this cost phenomenon. from the thermodynamics. The idea is that the driving force for a change of one component is a potential gradient only. Everything else is cross phenomenon. And you can calculate from the fundamental thermodynamics. So then basically you have to do this kind of calculations, but to be able to accurately calculate the entropy of the system, which we think this one may, at least so far, we have not seen anything we cannot predict it yet. Maybe I want to see here with any problems you guys have, we can work together to try to predict it. Okay, that's we call it emergent phenomenon. Okay, emergent phenomenon. And I hope work with Chris' group, double-sugar activity. That's my major goal here, which is something here. And I read a lot of paper about many body localization, which I think is covered by our approach already, because our approach doesn't matter what temperature. It's all this quantum states combination. Once it's already there, it never go away, even at a very high temperature. I think this is covered in my opinion. In terms of entropy, I'm not so clear. I have to review more about that one. If anybody knows better, it's great. We can discuss that one. Then I'm working with Will handling in our college and the entropy of the black holes. And I talk with many people about the biosystems. I talk about the forest, but unfortunately, my partner passed away 2019. He's a professor in the ecosystem. So I lost that direction now. I know that the Cavendish lab now do a lot of biosystem. Maybe some biosystem. Let me see how that works out. With that, one, thank you very much.
Thank you for this very interesting talk. Are there any further questions?
Yes, thanks for this very interesting talk. I was quite impressed by how you could how to say map out this emergent phenomenon by how to say separate the quantum and thermal settings. I was just a bit curious about this because I'm not an expert on it. I'm just starting to learn this quantum critical phenomenon. But in some cases, when people are talking about that, they tend to talk about the coupling between the quantum fluctuations and the thermal those things. I'm just a bit curious, like because in your model it's not be separated completely, and then you can still map out the emergent phenomenon. But in maybe other self-proposed theories, they tended to treat them as a coupled phenomenon. And for instance, I think in the ceramic oxide, there's some theory about, for instance, the phenomenon they could couple with the quantum polymer, something called the I think it's acoustic polar step.
Yeah.
We're just curious about, for instance, if you think about this, would you tend to treat them as something new and an independent property in your case, or?
That's a good question. For example, at the moment, we cannot calculate the mixed phonon together yet. We cannot. You see, we separate them, right? Don't put it back together. We'll get the entropy. We don't get the phonon dispersion anymore. So that's all. We don't know how to do that yet. That's what was told me yesterday, is that maybe when it compares to, can we just mix this different phonon spectrum together, use the probability? Can that generate the observed phonon? Because the observed phonon is a mixture of them, right? That's the first part. That's CP over T integration. That's basically include all the phonons together. We don't do that yet. But it's very important that the configurations you pick up has to represent the feature of the system. That's the key. For each nucleus, right? We have to really decide what structure to take in order to reproduce results. So that part is not easy. But with Chris's that random solution model basically means you don't need to know what a fluctuation would be. You can sample all of them, then put them back. I think it should solve all the problems, in my opinion. Yeah, because in that case, it's randomly generate structure. You don't predefine what structure would be. That means that in principle, you should be able to sample all possible structures, then do the energy calculation. You see, if the energies are close, they're important. If the high, that doesn't matter. You can just swim away, right? So that means if the sampling, if you can sample all those important states, the energy gap here depends on your temperature. It's really the KBT, right? KBT decide. So if you think about it, you want to do 1K, so it's the KB times 1. So that energy becomes very important. Okay, so it's really depending on what temperature you're looking at. If it's 1,000 Kelvin, right? So that would be 1,000 kb important thing. So it really depends on the temperature you're looking at. But for this approach, we can actually predict all temperature if you can sample all the configurations.
That's quite impressive.
That's why I'm so interested to come here. I think I want to work with kids, get two things, right? The structure and the superconductivity.
I was wondering, so is your theory agnostic to whether it's in when you're talking about superconductivity? Because obviously in the literature we're fairly good at predicting conventional superconductivity, but there's all this unconventional superconductivity, cuprates and ferrites. Would it be agnostic?
Yeah, I think that's actually I have one in my one of the proposal. It's for the cuprate. It's that you change the pressure. You see the temperature, the DC change from 100 Kelvin to 0, right? Just change the pressure. So if I look at that, that means when you change the pressure, you must have different configurations. They actually did experiment recently. Do you know what it did? What happens is that when you change the pressure, the oxygen ordering changes. So that means that when you change the pressure, you actually activate different configurations with the ordering. The ordering energy is very different, very small difference. Okay, so my thought is that if we can sum all the structure from the random structure, then you calculate all the energies, you can predict that transition at 0 Kelvin first. Okay, they can predict that transition which all occur. TC as a function of pressure. But you have to first decide what is superconducted by DFT.
Because I'm not sure DFT can predict that unconventional superconductivity. I
think it should be no problem. The reason is because if you think about superconductivity is emergent behavior, right? Yeah. It's a competition of different configurations. So one of them is conducting configuration, superconducting configuration. Some ones non-superconducting. They have many between. So it's this competition of the different configurations make it a superconductor, metallic, or insulated.
I think Pascal's point is that at the moment, so maybe in principle there's a DFT theory of unconventional superconductivity, but we don't have the code. We can't, we don't know how to do that now. But maybe what you're saying is all you've got to do is label the states.
Yeah, exactly.
You don't need to know. You just said it is a high temperature superconductor, maybe observed by experiment in this structure. And then you'll follow it. Then when you're mapping out the phase diagram, just mapping out.
Exactly. So that means, for example, taking Niobe as example, right? Now we want to add 4K, right? 4K. That means if we do zero K calculation, if you do at a given pressure, we know it changes from the superconductor to non-superconductor. Then we'll compare the structures. We say, okay, this is superconducting structure. That is not. Then we have some many in between. Then we just put them together. If we believe those are superconducting, then we just see how the percentage of population changes. If that population becomes lower than 50%, then you lose the continuity in space, then it becomes non-superconductor.
Thank you.
Are there any further questions? If not, let's thank the speaker.
Thank you, everybody.